Hello, everybody. I think we'll get started now. We talk about why computers calculate wrong, and that's something we say computers are very good in calculating. So that's exactly what they did in the early times and what they still do. But if we program them wrong or whatever, then they still don't do what we want. And this is especially about the core capability of computers, the numeric types, and of course in this conference using Java. So, anybody heard about the year 2000 problem? 16 years ago or 17 years ago, it was a big deal. And yeah, the younger ones maybe don't, but the older ones do. So the issue is, how many digits does a year have? And usually we say 2 because we are lazy to write, or sometimes we say 4, and maybe laziness is not always the best thing in this case. So let's see where we are in this world where we talk now. We talk about integers. So we have a quiz. We just take 2 billion, decimal 2 billion, so that's a number that can be expressed with an int. And then we add this thing to itself and we multiply it to itself. Anybody has any idea where we would get with this thing? So if you have an idea where this comes out, can you lift your hand or so? Sorry? Overflow, that sounds good, but let's see. It just gives this. It just gives you negative numbers without complaining. It's just like that. Okay? So that's important. And what we can know about this is the range of an integer is like 2 to the power of 31, negative of it to 2 to the power of 31 minus 1. And that's what can be expressed, and it just stays within this range, whatever happens. Yeah. So that's what we have to deal with. And the thing is that we have something called modular arithmetic. So if you ever went to some university classes about algebra in math or IT, in math or whatever, then maybe you came across this thing. If not, then you can see it here, because it's something that we actually know. Because if you look, have you ever, let me see. Sorry. Have you ever seen this device? It's a very familiar device, and that's actually what modular arithmetic is. So if you have like 10 o'clock and then you go 4 hours later, then you are 2 o'clock. Yeah? The same with the minutes and the seconds. So you have this silent overflow and it just counts on, but it resets itself. Yeah? And so we just think of this clock having not only 12 hours, but having 2 to the power of 32 digits. Yeah? And that's exactly what we have. So we can just rebuild the plus, minus, and times. This looks like a lot of noise, but actually it's not so hard. You know, this percent takes the remainder modulo something. Yeah, so you do division with rest. You throw away the quotient and you just keep the remainder. And this remainder thing that you have there, we normalize it so it comes into this range where the int is. And we do this with a long, yeah? And the long is somewhat bigger than the int. So for the moment, just trust me that it's right. And if you want to think, you can figure out that it's actually okay. But if not, you can do the same with BigInteger. And I did some example of it. So on the primary slide, you saw the GitHub account. You'll see it in the YouTube video if you like. And I Twittered it also. And there you can see examples. I did it with big int and long. Okay? So then we rebuild the addition, subtraction, and multiplication. So we just do these things. And then we apply this normalize method that puts it into the range of the integer. Yeah? And so we now use something bigger, but we force it to downgrade it to the int behavior. So we do the quiz now again with longs, but we do our own methods, yeah? And long would allow this result to be just 4 and then enough zeros, but here we have forced it this way. And let's see what comes out there. And you see it's exactly the same as the int, as you probably remembered, or the digits, but it is, yeah? So that's what we actually have. And the question is if this is really the right default, because as an application developer, this modular arithmetic is normally not what we are thinking of, but we have to know it's what Java does with the primitives. The long does the same, just you have more digits. Okay? So that's the weakness of the ints. Other languages, some of them throw exceptions, or some of them just go to a larger type or whatever, but here it's like this. So we can address this issue. We have to think about our ranges. So if we program something and then we use integers, integers in an abstract point of view, integral numbers, then we should think how large can they grow? And really think twice, because then sometimes they grow larger than we anticipated, but it should really work out and never overflow. And we can consider, does it really fit into an int safely? Okay. Or does it fit in the long? And if not, we can use the big integer. Yeah. But what you always think, you have to think about the intermediate results also. You might have a long calculation and the final outcome is very well in an int, but you multiply and divide and then somehow you get weird results. And these things are nice because they don't happen when we test with a simple 1, 2, 3 example. Everything works well. And then we go on production and then we do the end of year processing and then we get the big numbers, yeah? So maybe this is a thing to think twice. So in Java we have the good news. We have the big integer. We can usually afford the extra overhead of using it. What we can't afford is wrong results. Yeah, and there is an issue. If you want to dig deeper into this, you can discover the overflow of int by looking at the data before and after the operation. So if you like, you can investigate this, but I won't tell you now. The bad news is this big integer is a bit clumsy to use. You can't use plus minus times. You have to fall back to something like add and multiply, and then you don't see the formula. You have to spend some time to think. So that's that. The next issue is anybody of you using floating point? Who has used the double of float in the last 12 months? So we are not talking for nothing here. So I give you this quiz. We take a 1. Yeah? Then we divide it by something with 20 digits. Then we add 1. Then we subtract 1 again. And then we multiply it again. Then we should get something. What do you think what we get? Does anybody have an idea? 1 would be nice, but we get a 0. Yeah, that's that. So let's investigate why. So the double has a limited precision. It's actually quite a good, powerful type. It has 64 bits, so it's a lot of space, but we can always exceed it. And this 20 digits is a little bit too much. So it does something that is usually not so bad. It discards the least significant digits. It's the best it can do. But now the important information was exactly in the least significant digit, so it was discarded. So the question is, how do we deal with this? Again, I would say the most important thing is that you should know what you're doing. Yeah? Think what I'm doing here, and that's that. And if you do complicated calculations and you don't know yourself, it's no problem. But you should get people involved who know it. There's people who know numerical mathematics. You can find them maybe personal or in the internet or whatever. But look at it. Don't do wrong programs just because you don't look. And there's also the possibility to use other types than double. But there we get the next thing. So there is a possibility to use big integer or long. And actually you see many cases where you can just rethink the thing in integers. So for example, if you have money amounts, you can think of cents instead of euros. And then you don't have decimal points anymore, and then you are in much, much safer terrain. Okay? And the other thing is you can use something called rational. It's not a native Java feature, but you'll find libraries for that. And this rational thing is not so bad. It doesn't have rounding errors. You can just, as long as you add, multiply, divide, and these things, you can just do it, and it just becomes exact whatever you do. But there's, of course, issues. The numbers get huge. Each operation kind of doubles the amount of space that you use. So even if you do relatively trivial operations, you will always get huge numbers, and it will become slow if you do real big calculations. So that's something that you have to keep in mind. It's not the thing that you can just always use. And then the other thing is if you use doubles, sometimes you use these things, logarithm, sine, secant, and whatever, these transcendental functions, square root. And for rational, they don't they exist, but they don't fit in rational with the result. So that doesn't help us. And for that reason, we have to consider other options. So there is something called BigDecimal. And this BigDecimal is kind of the natural overflow if you just want to do something like double, but with more space. And you can use this BigDecimal, and you have something that is very, very valuable. You have an explicit control of the precision. So you can say, I want exactly this kind of rounding, and then you force it like that, and just don't get some default which might be wrong for you. It's, of course, much slower than floating point. And then when you look at these sine and cosine and these things, it's very unnatural. I haven't seen this combination in my live projects, but you can find libraries if you use that. And of course, again, you come across this issue. If you want to write plus, minus, times, you have to use these method names, and you don't see the formula without looking twice what it's really doing. But you can use it. There's another approach which is very interesting that is using intervals. So when you say you do floating point operations, you always round in some way. And you can round in both ways. And if you do that, then you can keep both results. And by that, you can at least say my result is within this range. You can be sure about that. And there's libraries about that, and you can go that way, but it's a little bit unfamiliar, and I just say it's possible, and it's useful if you really need it. We come across another quiz. You see this number 0.2, and now we have this %a. I have to explain you. That is the hexadecimal representation of it, of a floating point number. So what would we get there? Anybody has an idea? I just show you. It's this. And everybody knows it. I mean, floating point, you get 3.99999, and it means 4. So no reason to worry. But we have to be careful, because this is hex, and the 9 is not the highest hex digit. It's not this guy. So we are really in a bad area. And the reason is, in the decimal system, you can express everything that is a fraction where the denominator is dividing some power of 10. And here, we can have the same. So you see the 1/7, 1/3, of course, you get this periodic thing in decimal system. But here we have, of course, the binary system. And there it's not powers of 10, it's powers of 2. So only if we have denominators that are some powers of 2, then we get a nice representation. And the 0.2 is already a power of 5 in the denominator. And in binary system, it's no longer representable neatly. So that's the thing that we have to deal with. And you can just think that this is the same as in the decimal system, but it's just applying to other numbers. So the question is how we deal with it. And the issue is the decimal system in any way part of our business logic. In some cases it is, in some cases it isn't really. If we calculate bridges, for example, they don't care about decimal system, it just has to be stable, and if we calculate it in base 3 calculation and it's right, then it's right. And in that case it doesn't apply, but in other cases the decimal system is actually part of our business logic. For example, if we do use euros and cents and do use the euro as a base for whatever reason, then it's very much part of our logic. And we can rethink, of course, in int and long again. That's the most obvious approach. We can move to BigDecimal, and then we are in decimal system, then we are clean with this. So the only thing that I want to keep in mind is never ever use double to express money. Yeah? That's just a no-go. Use integers, use BigDecimal, whatever, but double is just not right. Okay? I've seen it, but please don't. That's it. So I guess I just repeat. There's 3 issues that I told you. The one was the integer. It uses modular arithmetic without telling you. The one is the double. It just has a limited precision and it discards the lower end. And the other thing is the double. It uses binary system internally. And so if you have something that's neat in decimal system, it doesn't have to be nice in binary system. So that's everything I could tell you. And then we have a little bit of time for questions if you have some. Otherwise, yeah, I wish you good luck for the rest of the conference. Okay. And here you can see the GitHub also, yeah? Where you see the examples for it. Yeah, hello?
There's also the strict FP, you know, in fact, Java is supposed to run anywhere, not just on x86 architecture.
Yes, the strict FP is basically just tweaking the behavior of the double a little bit, and it's enforcing it that it's independent of the hardware everywhere the same. And actually, if you look at the source code of the floating point implementations, you see that it does pretty much things like strict FP also in other areas where it doesn't have to. But that's if you really want reproducible behavior, you can use strict FP and you pay a penalty in terms of performance and you're sure it behaves the same on each VM. And if you don't use strict FP, then you can kind of allow JVM to cut corners and to be a little bit faster and to be pretty good results. Okay?